Welcome to Ask and Learn.
We want to use some kind of CAS software to graph the function f of x is equal to the square root of 5 times sine of x plus x when x is less than or equal to 20. So I went ahead and did this here. So the first thing we might want to do is to just write down where these intervals are, because later on we're going to want to find the first and second derivatives and determine intervals where the function is increasing, decreasing, as well as intervals of concavity. And if we already know what our domain is, it'll just make making those intervals a little bit easier. So let's go ahead and do that really quickly. So this first interval here is going to be about negative 4.906 to about negative 4.105. Then our next interval is going to be 0 to 1.4105. And then it'll be about 4.906 to 20. And before we actually look at the first and second derivatives, you might notice that we have a bunch of points that we should possibly see for our first derivatives. And in these first two little pieces, it doesn't really look like concavity changes, but then maybe around these points here, it looks like we have change in concavity. So just some points we might want to look out for when we're looking for our intervals of concavity and where the function is increasing and decreasing. Right, so I went ahead and plugged that in and found f prime to be 5 cosine x plus 1 all over 2 times the square root of 5 sine x plus x. And I went ahead and found where these intercepts were. And now what we can do is, let me go ahead and scoot this up a little bit so I have some more room to work underneath. Let's figure out if these are going to be maxes or mins, and at the same time we can kind of go over what our intervals of increase and decrease are going to be. So first, remember f prime of x, if it's strictly greater than 0, then we know the function is increasing. And if f prime of x is strictly less than 0, then we know the function is decreasing. Right, so to the left of negative 4.511, it's positive, so I know it's increasing into this point, and then it's going to be decreasing afterwards. So we know this is going to be a local max. Our other intercept, well, it's positive to the left, so it's increasing into it, and then it's negative after, so it's decreasing after, so we get a max there. Our next intercept, again, it's increasing into it, and then decreasing after, so we have another max. And now our next point, well, now this one's going to be a minimum because it's decreasing into the point and then increasing afterwards. So min, our other point, well, it's increasing into it and then decreasing out. So this is going to be a max. And then our other function, or our other intercept here, well, it is decreasing to the left, increasing to the right. So that means we have a minimum here. Now that we have that, we can just go ahead and write down all of our intervals since we already said where it's increasing and decreasing. So from negative 4.906 to negative 4.511, and then from 0 to 1.722, and then from 4.906 to 8.055, and then 10.794 to 14.379. And then our last interval where it's increasing will be 17.077 to 20. Kind of long interval, but luckily for us, the decreasing one won't be as long. Or actually, I guess it will be just as long, unfortunately. All right, so it starts to be negative after negative 4.511, and it will stay that way until negative 4.105, and then unioned with, and then from 1.722 up until about 4.105 union, and then after this 8.055 to 10.794, and then our last interval where the function is decreasing is about 14.379 to 17.077. Right, so we found our maxes, mins, as well as where the function is increasing and decreasing. And if we just kind of go back and look at these values, you see that they match up with all these little lines that I have drawn on this graph. Right. So at least good to know our intuition gave us some of the answers. Now, I went ahead and found the second derivative and then graphed it as well and found the intercepts. And just so we can kind of look, so to the left of 9.602, the function is going to be concave down. So let me just go ahead and write this. So remember, when f double prime of x is strictly greater than 0, it is going to be concave up. And when f double prime of x is strictly less than 0, the function is going to be concave down. All right, so now let's just first go ahead and find our points of inflection, and then after that we can write our intervals where it will be concave up and concave down. All right, so at 9.602, well, to the left of that, the function is going to be concave down, and to the right is going to be concave up, so that is a point of inflection. To the left of 12, it should be concave up, and to the right, it's concave down, so this is also going to be a point of inflection. Around 15.8, it is concave down to the left, concave up to the right, so we have another point of inflection. And our last one will be concave up to the left and concave down to the right, so that will also be a point of inflection. Now let's go ahead and write our intervals. So we're concave up when f prime of x is larger than 0. So that starts at 9.602, and it'll go until our next intercept, 12.252, and then we union that with 15.811 until 18.651, and that will be all where our function is concave up. Now it's concave down, so it's concave down on these two intervals here, which are going to be negative 4.906 to negative 4.105 union, and then 0 to 4.105, and then from 4.906 to our first x-intercept being 9.602, and then it's negative again around 12.252 until 15.811, and then our last interval will be from 18.651 to 20r endpoint. And so if we were to look for those inflection points on the original graph, those four match up with what we said, and we can also see those first two little hoops are going to be just concave down, and then after that it just kind of follows that interval pattern that we had. So we found everything we wanted for this problem.